Good evening, everyone, uh, and I welcome all of you to the first live session of the course Thermodynamics. Uh, so, this will be an interactive session uh, wherein we will be solving some of the questions related to the concepts that are being discussed in the class. So, at any point of time, if there is any issue in understanding any particular step or overall any concept that we will be discussing, you can type in the chat box or you can directly ask. So, just let me. So, can somebody please let me know if the presentation screen is visible or not? If anybody can just unmute and let me know.
No, it's good, sir. It's good.
Okay. And
Yes, it is visible.
okay. And if any of you see that somebody is waiting in the lobby to join the meeting, please let me know because the when I go to the PPT screen, the meeting screen won't be visible anymore to me. So just let me know. So let us start with today's session. So first to introduce myself, I am Abhik Dev and I am presently doing my PhD research work in the Department of Mechanical Engineering at IISc Bangalore, and I shall be one of the TAs who will be taking the live sessions of the course Thermodynamics. So in this we will be discussing and some small questions related to the concepts that were discussed in the previous class of the theory course, so as to help you with the assignments or and also with the um, overall theoretical concepts that are being taught. So at any point of time, if you have any doubt, please do ask so that we can make it a mm, interactive session, which is actually supposed to be its sole agenda. And this session will be repeated every Friday from 6 to 8 p.m. So please try to attend it. Uh, Hopefully, it will be helpful for all of you. Okay, so today's session is mostly focused on the concepts, the very basic concepts with which the course of thermodynamics will start. So, concepts like the system, what is a system, and then what is a surrounding, what is a boundary, what is a control mass system, what is a control volume system, and the related problems, related concepts associated with these. So these are very basic. So most of you, I am certain that most of you have already understood what all are these. So we will just be revising these and I mean in form of some of the numericals that we'll be doing or theoretical questions that we'll be solving. And at any point of time, if you find any doubt, then please do ask. So, so let us start with a very theoretical problem. Um so there are 10 this is like a match the following thing. Uh, there are 10 uh, what we can there are 10 words that we are given here, like 10 particular mm, identifiers, like what is a boundary, what is a closed system, and there are 10 one word definition kind of things which will be attached to this, so we have to match them. So let us start with the concept. What is a system? So because to understand what is a boundary, we have to first determine what is a system. So okay. So what is a system? So whenever we are concerning ourselves to a particular quantity of matter that we are studying, so it can be a box of stuff, it can be any it can be any particular collection of material with a hypothetical covering, or anything that we are studying, which is the main on which the particular quantity of matter on which our study will be focused, that is called the system. So let us consider that this is a particular quantity of matter on which our study will be focused, so this will be the system. Okay, so this is basically our matter of interest. Okay, so this is being studied, okay, which is studied. Okay, minute. I think multiple people are waiting to join. So, okay, and there will be the everything that is external to the system, like everything external to the system with which it will be interacting with. Say this is a let us consider that this is a heated mass of gas, then it will be interacting with the surrounding by releasing heat to the surrounding. Or suppose this is a motor, electric motor, and it is giving out an electrical work that is driving a vehicle, then this everything external to it will be surrounding with which it is interacting by transfer of heat or work or maybe mass transfer. So but anything external to it, so this is surrounding. So surrounding is what is outside the system, with which system interacts. So now between the system and the surrounding, there may be a physical boundary, physical separation between the two, or it might be considered, it might be a hypothetical one. That is, we are considering by ourselves an imaginary one. So this separation, this is a separation between system and surrounding. So this separation, it can be a hypothetical one. Okay, like suppose we are considering a collection of gases, or through a pipe a liquid is flowing, then if we are considering a particular fraction of that liquid, then it is, there is no physical boundary, but it is a hypothetical boundary that we are assuming for the analysis. So it can be a imaginary boundary also, imaginary separation also, or it can be a physical one. Like suppose we are considering we are considering the analysis of an electrical motor, and the boundary of the motor, the wall of the motor is considered as a separation with the surrounding air. Then this is the physical boundary. So it can be physical or it can be imaginary, but whatever thing that is separating the system with the surrounding will be considered as a boundary. So what is a boundary? Boundary is what that distinguishes the system from the surrounding. So boundary distinguishes the system from the surrounding. Okay, so this boundary, so this is the number 1, it is matched with I, that is distinguishes the system from the surroundings. So okay, so till now if there is any doubt, please do ask. So if there is any doubt till now, please do ask. Okay, so the next part. So what is a closed system? Now there are different kinds of system that we'll be focusing on. So system. System is anything that we are on which our analysis is focused on. So now if a system can only transfer energy with its surroundings, that is, if a system can interact with its surrounding only by the transfer of energy, but mass from the system cannot go out to the surrounding, or it cannot flow into the system from the surrounding, then it will be a closed system. That is, only energy can flow. So only energy can flow in or out, but mass cannot flow in or out, then this will be a closed system. Okay, now if both energy and mass can flow in or out, then that will be a open system. An open system, that is, the system can interact with its surroundings by both the transfer of mass and energy, then that will be an open system. So an open system can be, the open system can also be, it is usually also called a control volume. And a closed system is also called a control mass. Why control mass? Because the mass is fixed here. At any instant of time, whatever the mass we considered at the initial point of time, it will remain fixed. Whatever it, even if it is flowing, then the boundary of the system will also be changed as it is flowing. So we are considering the entire mass, and nothing is going in or out. So the mass remains fixed, and hence it is a controlled mass system. But in control volume, it is like we are fixing a region in space, and that is, we are fixing a volume in space, and through it the mass can go in and out, the energy can also go in and out, and we are analyzing it. So that is a control volume. And the another type of system is the isolated system, that is, neither energy nor mass can flow in or out. So that is a isolated system. It is like that the system overall does not interact at in any way with the surrounding. Like although in practical cases there will be always a transfer of energy, However, supposedly we are considering that there is no work transfer and it is very perfectly insulated, then there will be no heat transfer. So and if it is a closed system and if it is perfectly insulated and there is no other work transfer, then it can be considered that this is a isolated system. So what is a closed system? So a closed system is a fixed quantity of matter. So a closed system is a fixed quantity of matter. And what is a control volume? So a control volume will be a region of space through which mass may flow. A region of space through which mass may flow. So like this is 2 will be G and 3 will be B. So I hope till now everything is clear. If there is any doubt, you can please ask. Okay, so I am taking that there is no doubt till now. So now extensive and intensive properties. So what is an intensive property? Intensive property is something which is independent of the mass, like pressure and temperature. So let us consider a system which has a particular mass m, and we can consider that each of the this domain, this system can be divided into a set of subsystems of masses m1 m2 to mn, such that the total mass of the system m being the sum of these individual masses. Now intensive property will be such that if we consider the property of any particular subsystem of mass m1, let the property be p1. Okay, and of mass m2 the property is p2. So the total mass and the total property of the system, that is of the mass m, will not be the sum of the individual properties of the individual subsystems. It will be a particular property p system which might be equal to the individual subsystems, or might be a combination of the two, like combination of all the systems, but it won't be a sum of all the property values. Like supposedly this is a system and there are different points, and let us consider the temperature. So T1, T2, T3, T4 and Tn. Okay, so the total temperature of the system will not be a sum of T1, T2, T3 and Tn, but it can be such that at this region the temperature is lower and at this region the temperature is higher. So an average of this can be a temperature of the system, or if the temperature is uniform throughout, then that the same value, that is it is T1, or that is the temperature of the system will be, it will be equal to T1 or T2 T3 individually, but it won't be a sum of the this thing. So this property does not depend on the mass of the considered system. Hence, it is an intensive property. So properties which are independent of mass. Independent of mass of system. Okay, like temperature, the pressure, etc. Okay, so now what is an extensive property? So it is a property which will be depending on the mass. Like if we consider the previous example, suppose a property say A1, A2, AN. So these are like three, if we are considering three systems, three subsystems of the system, then the total property will be a sum of these properties. Okay, so this property is dependent on the mass of the system. So the properties which are dependent on the mass of the system. System. Okay, uh, an example is of extensive property is a volume. Okay, so can anybody give me an example of some other extensive property? Anybody? Can you please unmute and give me an example of another extensive property? Anyone? Otherwise, I mean, it is difficult to understand if you people are catching up to it or not. So, uh, please, anybody, any other extensive property?
It is weight.
Well, not exactly
Hello.
weight. Yeah, yeah. Hi, Mohit. Right.
Yes, sir.
Yeah. Not exactly weight, but the mass. The mass itself will be an extensive property. So obviously, if we multiply it by the acceleration due to gravity, but uh,
Yes, sir.
uh, essentially weight is not considered a property of a system. So the mass will be an extensive property. Yeah, good. And so somebody has raised a hand, Varun. So yeah, go ahead. Uh, Varun Kumar, if you have any, do you have any query? Please do ask. Okay, so another extensive property is,
Sir?
yeah, hi.
Yes, excuse me, sir. Hi, extensive properties. Another one example, length,
Another one is, sorry.
uh, size, length, sir. Length or size.
Okay, so see, the length or the size is essentially qualified as the a fraction, a portion or a measure of the volume. So you cannot specify for a three-dimensional object with a particular mass. It is not essentially a length, a single length. It will be like a dimension in three directions. So it will essentially be the volume. So other extensive properties can be like the energy, like the internal energy of a system. A particular mass, it has a particular internal energy, right? So suppose if we are considering a heated volume of gas, so that mass, if we are considering half of the gas, then it will be having a lesser value of internal energy, like half the internal energy, since the mass is getting half. So that is a extensive property. And enthalpy, so you will be dealing with these terms like internal energy, the enthalpy and entropy, everything in the future classes. So these terms are all extensive properties. And a very to begin with, internal energy, or the energy that a particular mass has uh, at a given point of time, that energy, internal energy, is also an extensive property. Now, other than the temperature and pressure, can you give me an example of any other intensive property which is not dependent on the mass? Any other intensive property?
Density, sir.
Sorry?
Density.
Yeah, density. So what is density? Density is, what is the definition of density?
Mass upon volume.
Yeah. So basically we are taking mass per unit volume. So it does not depend, like see, both mass and volume are extensive properties. So when we are taking a ratio of those two, we are getting an intensive property. So from this you can come to a important conclusion that all specific properties, like when we supposedly in most of the cases we will be dividing it by volume. So density is like the inverse of the specific volume, like, so volume by mass. So when we divide an extensive property by another, by in most cases the mass, the another extensive property, so it becomes a specific quantity. So this, all these specific quantities are all intensive properties. So specific volume, although just previously I mentioned that internal energy is an extensive property, but specific internal energy, when you divide this internal energy by the mass, the specific internal energy will be an intensive property. So all these specific quantities are intensive properties. So I hope it is clear. So let us get going with the discussion. So extensive property, what will be an extensive property? This enthalpy, enthalpy, internal energy. Okay, just a minute. So somebody wrote that mic is not coming. So is it audible to everybody now, or is there any issue with the mic? I mean, with the
Yes, sir.
it is coming, right?
No
Yes,
issue,
sir.
sir. Yes, sir.
Okay, okay. And what is the
Yes.
difference between a closed system and an intensive property? Okay, so a closed system is like what? So for that you need to know what is the difference between a system and a property. Like a system is a particular mass on which our attention is focused. Okay, like it can be a glass of water. Okay, so let us take the example of a glass of water. Water. So suppose this, the amount of water in it, we are considering that. So this is a our system. So this will become our system. Okay. Now this glass of water, the water that is in the glass, that is in the system, will have a particular characteristic. What are the characteristics? Like it will be having a particular temperature. Okay. It will be at a particular pressure, which is in equilibrium with the atmospheric pressure. At this point, the pressure of water will be equal to the atmospheric pressure at the top surface, and it will be having a particular temperature. So these values, these are the properties of the system. Then it will be having a particular volume also, volume that it is occupying within the glass. So this volume, this is an extensive property of the system. These are the intensive properties of the system. These are basically the characteristics of the system. These characteristics of the system are used to define what is the state, that is what is the present nature or state of the water in the glass, that is what is the present state of the system, are being defined by these properties. So these are the intensive property. These are independent of the mass. Like if we take 1 liter of water, it will be having from the same source. If we are taking 1 liter of water, it will be having the same temperature and pressure. If we are taking 500 milliliters of water, then also it will be having the same temperature and pressure. However, for if we take 1 liter of water, the volume will be different. It will be 10 to the power minus 3 meter cube, and if we take 500 milliliters, then it will be 0.5 into 10 to the power minus 3 meter cube. That so this volume depends on whatever mass we are taking. So these are the this is an intensive property and this is an extensive property. And if we are considering that since water is not leaving this boundary that we are considering, so this will be a closed system. So this is a property and this is a closed system. So does it answer the question of what is the difference between a closed system and a intensive property? Okay, so I hope it is clear.
Yes.
And okay, so and regarding a good textbook for thermodynamics, you can start with Thermodynamics by P.K. Nag and Thermodynamics by Sengel, uh, or you can, I mean, I think so. Those two will be quite a good book for starting. Basically, Thermodynamics for P.K. Nag will be quite helpful for the beginners. And the slides, okay, the slides will be made available, so there is no need actually. The videos will also be uploaded, so I don't think that there is any requirement for the you to note down. Basically just try to understand the concept, so it will be better. Okay. The textbook, uh, actually we are not supposed to, we do not have any email IDs or any such way of interacting with you people. So the PDF is very easily available. You just Google it, that Thermodynamics by PK Nag. It is very easily available over Google. You can easily download it. So I think so it will be helpful. You can directly download it. And if we are any particular college, then most of the college libraries also have the book in hard copy. So you can also do that, or if you want that in a soft copy, it is just a Google search away. It will be easily available. It will be easily available for you to download. Okay. So Hemant, is there any doubt?
Good evening, sir.
Yeah, good evening.
Hello.
Yeah, hello. Yeah.
Sir, I have a doubt regarding adiabatic wall, sir.
Okay, adiabatic wall. So we have not yet gone to that, but do ask.
Sir, sir, let me clear, let, I have one doubt, sir, that
Yeah.
in thermosteel is
Hmm.
a bad conductor or adiabatic wall, sir?
Thermosteel.
Thermosteel is bad conductor or adiabatic?
Okay,
Yes,
so
sir.
I do have to ask
Is
you,
bad
what are you defining a bad connector as? Bad connector by meaning bad
bad
connector, you
conductor
are
of heat, sir?
so it is mainly to define that property. We basically take the help of conductivity. Okay, so we don't say it as a bad connector, we would say it as a bad conductor. Okay, so it is basically a whatever you ask, it is
Yes,
a
sir.
good question. So let us just so suppose, let us see. So this is, let us consider a hot liquid. Okay, and this is air. So there is a separation between the two. Now, if the heat from the hot liquid to the air is getting transferred, that in scientific terms we call it as conducted. Okay, so if it is getting transferred very
Yes, sir.
easily,
Yes,
then it is a good conductor. However, if it is a it is not transferring the heat very easily, then it will be a bad conductor. Okay, so regarding the thermosteel, so you are considering the you are asking about a steel, or you are considering the thermosteel flasks that we use. Are you asking about the thermosteel flasks that we
yes,
use,
sir.
or you are asking about the steel?
Yes, sir.
So see first the steel. Okay, so
No, sir,
if it
I'm
is a
asking about thermo.
steel flask, okay,
Yes, sir.
just let
Yes, sir.
me clarify it. So if you consider steel, okay, so it has a high conductivity, so it will conduct the heat easily. So it is not an adiabatic wall, it is not a bad conductor of heat. But when you are saying about the thermosteel, what happens is that there are two layers of steel. Okay, what is inside and what is outside. Okay, and in between there is either vacuum, at I mean not vacuum, it will be a low pressure air. So air is a very bad conductor of heat. Okay, so the heat from the thermosteel on the
Yes,
inner
sir.
surface cannot go to the outer surface. Okay, so in that way the system is kind of insulated, or uh, what we'd say that this combination of the system will become a bad conductor of heat. And regarding the adiabatic wall, what you are saying, for adiabatic wall there is no transfer of heat across it. Okay, so essentially to make an adiabatic
Yes,
wall,
sir.
we generally provide an insulation. So like what you asked is a thermosteel, the thermosteel wall can be considered as an adiabatic wall, but the thermosteel, combination of the two, it is like a bad conductor is used for making an adiabatic wall, so that there is no transfer of heat across it. So does it?
Sir, another small clarification, sir.
Yeah, yeah. Please go ahead.
It's a small
Yeah,
clarification.
yeah, please go ahead.
Like we know that uh, like in methods of heat transfer, basically we are having three major one: conduction, convection, and radiation.
Yeah.
So basically, in adiabatic wall, does heat transfer in the form of radiation may takes place or not takes place. I want that just
No,
clarification.
so adiabatic world means no heat, the heat transfer will be zero. It can be conduction, convection, radiation, everything will be zero in an ideal case. It won't be zero in any practical case, it will be close to zero. Okay, so in practical case, but there will be no
Okay, sir.
radiation heat transfer, there is no conduction heat transfer, there is no convection heat transfer. However, in the practical cases that we are dealing with, in most of these cases the temperature inside or the temperature that we are trying to insulate is quite low, and the as we know that the radiation heat loss will be it becomes significant only when the temperatures become significantly high. So we just provide a bad insulator. However, it is not a necessarily indicator that the radiation losses will be low because of the addition of the insulator. These will be low because in most of the practical cases the temperatures are significantly low, so the radiation losses will be low. There will also be a convective heat transfer from the outer surface of the insulation, so that will also be present. But when all of these are very low, then only we can consider it to be a adiabatic. This is not like it, nothing will be perfectly adiabatic, there will always be a heat transfer across it, however insignificant it might be. But if it is closing to zero, then we will consider it as adiabatic. And to answer your question, there will be no radiation heat loss also. I mean, this Q encompasses conduction, convection as well as radiation. So does it answer your
Okay,
query?
okay, sir. Thank you, sir.
Okay,
Yes,
okay,
sir.
yeah,
Thank you, sir.
okay, okay, okay. So
Hello.
yeah,
Good
hi,
evening, sir.
yeah, good evening. Yeah, please go
Sir,
ahead.
explain problems.
Yeah,
Problems explain, sir.
so you were
Problems upon thermodynamics explain, sir.
okay, so yeah, we will be going to that. What all have been discussed, like in the this class will be primarily focused on the concepts that were discussed in the first week. Okay, so I mean this is very introductory. So gradually, when you will be going into the thermodynamic problems, in the next week we will be discussing the questions related to that. So although I would be very much interested in going directly to the numericals, but I mean we are advised against it because we have to go like week wise. So anyway, there are a few numericals, very basic numericals in today's session as well. So just please wait, we will be going into it. So like
Sir, which is the good textbook for solid mechanics?
okay, solid mechanics, like for solid
Strength of
mechanics,
materials.
strength of materials, like that I don't think I should be the one to answer because I am not the teaching assistant for strength of materials. So which course are you taking for strength of materials?
There is no course available, sir, in NPTEL
Okay, then
here
but
for strength to
you may ask your seniors, but I don't think I should be the one to answer you this because like this is a course for thermodynamics, so I should not be the one to answer you. I hope you understand. So any good textbook, you can ask your seniors which they are following. I think that will be helpful. Okay, so
Thank you, sir.
yeah, sure. So let us go ahead. So extensive property, its value is for an entire system is the sum of its values for the parts into which the system is divided. So I hope it is clear to everybody. So it will be the point E. And what is the intensive property? It is independent of the size. Extent of the system. Okay, independent of the size and extent of the system, and may vary from, it may vary, see, the temperature at different locations can vary, so it may vary from position to position, and it may vary from position to position within the system. So here is a maybe H. So intensive property. Now what is a process and what is a property and what is a state? So property we have already discussed. So what is a property? Property is, let us start with the process. What is a process? So suppose a particular quantity of matter, it is transforming from a particular temperature to a particular temperature. Say suppose a glass of water is cooling from 100 degrees Celsius to say 30 degrees Celsius by the loss of heat. So this process from 100 degrees Celsius to 30 degrees Celsius, that will be a process. So this is a transformation. It is basically a transformation from one state to another. Okay, so this is the answer to that. And what is a property? Property is basically a macroscopic characteristic of the system, like temperature. So it comes from, the temperature is a macroscopic quantity, and like pressure, it is also a macroscopic quantity. How is it coming? So internally, if the molecules of a gas, how so with the force that they are colliding against a wall per unit area, that force per unit area gives the pressure. So that interaction of the molecules with the wall is a microscopic aspect, whereas this property that we are quantifying it, that is a macroscopic, like a the sum total, the final effect of these interactions of these molecules that we are considering. So it is like a macroscopic characteristic of the system. Macroscopic characteristic of the system, to which we assign a numerical value, and this numerical value, it does not depend on what the state of the system was in the previous time. So like the temperature, we are giving it a value, suppose it is a temperature of 100 degrees Celsius. Now it does not depend on what the temperature was like at a very particular 2 minutes back, which we were just concerned about the fact that by some process from 2 minutes back the temperature was supposed T or 200 degrees Celsius, it has now come to 100 degrees Celsius. So it is not dependent on what the value was previously. It depends at any particular instant of time what is the value, so irrespective of the previous behavior of the system. So it will be J. And what is the state of the system? so by these properties, these microscopic characteristics, we are defining the condition of the system, that is in which condition the system is presently existing. So the condition of the system described by its properties. So this is this one. Then the surrounding we have already explained. Surrounding is everything that is external to the system, that is everything that is external to the particular quantity of matter that we are studying. System, so will be F, and what is a system? System is finally everything that we are studying. So I hope it is clear to everybody, and if there is no is there any doubt? If there is no doubt, then we will move on to the next problem.
Excuse me, sir.
Yeah, hi. Yeah, please go ahead.
So what is difference between state and phase, or it is no relation between them?
State and what did you ask?
Phase.
Okay, phase.
Phase.
Okay, yeah, phase.
Phase.
Yeah, I got it. Yeah, so what is a state? Like a system can be in a particular, suppose we are again considering a glass of water. So it is in a state of suppose we are considering a glass of water, and it is at 70 degrees Celsius and 1 atmospheric pressure. So these conditions, it will determine what will be the phase of this substance. Like had it been 110 degrees Celsius, it won't be in the liquid phase, it will be in the vapor phase. So these properties, these states, essentially to say that these states determine what will be the phase. Phase is like a physical quality, like in what is the physical characteristic of the system, and state determines what will be the physical characteristic. So state does not consider its I mean the state doesn't concern itself with the phase, but the phase will be determined by the state of the system. So does this example help you to understand what is the difference?
Yes, sir.
Okay, so then let us go
Means,
ahead.
sir,
Yeah,
solid.
yeah, go ahead.
So solid, liquid, gases, these are phases,
Yeah, these are phases, but see, the solid can be at a
not
temperature.
state.
No, not they will inherently have a state value assigned to it. Like a solid can have a temperature T1 and pressure P1. Now it is being heated, it remains in the solid phase itself, it will be having a temperature T2 and the pressure P1, say the pressure is not changing. Then these two are the states. So a particular phase can be this physical characteristic of the system. These can encompass different state values as it moves from one process to another. But at a particular time when the temperature will be so high that it will start to phase transform, that is it will change the phase, then I mean, like you can consider the state is a continuous variable, like the temperature is continuously increasing. So these characteristic, like the temperature, it is a characteristic of the system. but phase is depending on this value, like what is the temperature and what is the pressure, or what will be the physical manifestation of the system. So to answer your question, solid, liquid and gases are phases, but they will inherently have numerous states assigned to them, like they can have numerous states assigned to them. So is it clear?
Yes, sir.
Okay. Okay, so let us then move on to a problem. So all these problems will essentially be theoretical problems only, not numerical ones. So let us consider the boiling of water in an open vessel. Okay, so with the heat applied from bottom. So like we are keeping a open vessel on a stove and it is being heated from the bottom. So we have to identify what are the mass, heat and work flows of the system, and if the system is in equilibrium or if the system is in steady state. Okay, so we will be defining these terms. So what can we say now? We considered that for this analysis we are considering that only the liquid fraction of water that is remaining in the vessel as a system, that is we consider the liquid water to be the system. See, the choice of system is also very arbitrary. You have to choose the system so as to suit your problem at hand. So presently the water, it will be changing phase to the vapor, and it is the vapor will go to the air. So if we had considered the entire system, then we will have to analyze how the vapor is moving to the air also. Or if we had considered a system that is like encompassing the boundary of the vessel also, so the heat conductivities of the vessels will also come to picture. So our system is very, we can consider it to be a very simple system by considering that only the liquid fraction of water at any instant is the system. Okay, so just let me draw this. So from the system there will be, these are the vapor. So when you heat water, after a particular time it will start to evaporate. So this is the mass of the vapor that it is going. Okay. Now what is the, we have to identify what is the mass, heat and work flow of the system. So what is the mass flow? See, there is no inflow. Is any water entering the system? No. So there is no inflow. Inflow, there is no inflow. Outflow, as the water is getting evaporated, a fraction of water at any instant is leaving this system. So the mass is going out of the system. As water evaporates, from the top surface, there is an outflow of mass at top surface. Okay, so this interaction, this mass interaction, that is mass going out, it will be at the location where it is going out. So the outflow of mass is assigned to the top surface. Now workflow. What is work? So work is anything, suppose a transfer of energy to the system such that this transfer of energy can be equated to the lifting of a weight. So in these there are different forms of work, like there can be a displacement work, there can be electrical work, there can be several other forms of work like the surface tension work and so on. So here no work is being done on the system, so there is no work in or out of the system, so no workflow in or out of the system. Now going to the heat flow. So what heat flow? So heat input to the system. There is a heat input to the system from bottom, and outflow will be, see, since the temperature of the water is rising, so there will be heat losses via these walls. I mean, it will lose heat to the walls, then that heat will be lost to the surrounding air. Then from the top surface there is a heat loss accompanying the mass that it is being carried out with, like the heated vapor is being going out of the system, so that will be, and that will account for another heat loss. So the significant heat losses will be, the significant heat losses will be from the top and the side surfaces. See, this is a relative analysis. So you can see that at the bottom surface there is a significant heat coming in. So the at the bottom surface also the temperature will be high, and there might be some heat that is there is an interaction from of this layer of liquid with the bottom surface, causing a loss of heat. However, that amount or fraction will be insignificant compared to what is going inside. So at this surface we will only consider that the heat is coming in and not going out. Okay, so this is what the heat flows will be. And what is the system in equilibrium? Now what is a system in equilibrium? So we define a thermodynamic equilibrium in such a way that uh, it will be considered as a thermodynamic equilibrium when it has thermal equilibrium, mechanical equilibrium and chemical equilibrium. So what is thermal equilibrium? That is, there is no temperature difference from one point to another within the system and from the system with the surrounding. This is the thermal equilibrium. Mechanical equilibrium is that there is no significant pressure difference between the system and the surrounding, which might result in some spontaneous expansion or compression. And there is another is the chemical equilibrium. So at any instant of time there is no chemical reaction going on inside the system which would result in the formation of some species or result in the generation of some heat. So this is the chemical equilibrium. So when all these three equilibrium are present, we will consider it to be a thermodynamic equilibrium or equilibrium in general. So here the system is being heated continuously. Okay, so you can see that since the heat is being supplied continuously, so from the bottom surface the temperature will be gradually reduced to the top surface. Okay, so this will be at a maximum temperature, then it will gradually reduce, the heat will pass through this, and it will be a bit lower on that at the top surface. So there is a the system itself has difference in the temperature between the 2 points. So the system is not in thermodynamic equilibrium. So there will be thermal gradients within the system. So system is not is in, so system is not in equilibrium. Okay, now but if you see, if the heat supplied is at a very slow rate, so the heating of this will be very slow, so that the temperature gradient from here to here will be very slow as well. Okay, and there is a heat loss from here. So it is, if it is such that the heating is so slow that the temperature gradients within the system is significantly low, then it can be considered as a quasi equilibrium state. Like at a very small instant of time, the system appears as if it is in equilibrium, as if there is no significant thermal gradient within the system. That is, it appears as if it is in thermal equilibrium. So it is like it is approaching an ideal process. So in that case, it will be considered as a quasi equilibrium state. Now a steady state, like what is a steady state? Steady state is when the properties of the system, all these properties of the system are not changing with time. However, you can see that when it initially started heating, say the water is being heated from 30 degrees Celsius. So initially the temperature of water won't be directly 100 degree. It will gradually increase from 30 degree to 35, 40, 50, 45, like this to 100. So it is changing with time. The temperature at any given location is changing with time. So the system is not in a steady state. Okay, so we can write it as, since the system is being continuously heated, so temperature at any point at any location changes continuously with time. So system is not in steady state. However, it will eventually, if it is such that the heat that is coming in is exactly equal to the heat that is being lost, then the temperature at any instant will not be significantly changing, because whatever heat is coming in is being transferred or is being lost. Then in that case, it can approach a quasi steady state. However, in real case, as I mean, after this, like if we are saying that how will it reach a steady state, like when the heat that is being input is not able to change the temperature at any particular location from time to time, because the heat that is being supplied is being equally lost from that point. So in that case, the temperature will not change significantly over time, and we can say that the system has attained a steady state. So is it clear to everybody?
What is the difference between steady state and equilibrium?
Okay, so equilibrium is something which is a essentiality, which is a necessity for the system to be in steady state. Like if there are no, or we can say so like in equilibrium, how do we define? Suppose at from this point to this point there is a temperature gradient, that is the temperature is different, then there will be a flow of heat from this point to this point. So till the temperature at these 2 points become equal, there it won't be in equilibrium. That is, the heat flow from a region to another region has not stopped yet. There is some heat flow that is going on inside the system. So that is a thermal equilibrium. Like it can you can consider equilibrium to be the possibility of a spontaneous process. Like if there is a temperature gradient, there will be a spontaneously the heat will flow from a region of higher temperature to a region of lower pressure, or if there is a pressure gradient, there will be a flow from a region of higher pressure to a lower pressure. So that is like a spontaneity of the process. Like if there is no equilibrium, there will be a there is a possibility that a process will happen. In steady state, like in steady state, the temperature at this region is not changing with time, the temperature at this region is also not changing with time. So there can be a heat flow between them. However, the temperature supposedly this is the temperature is at 100 degrees Celsius and this is at 30 degrees Celsius. There can be a heat flow between them. However, due to some replenishment of heat, say another heat source is coming at this region, or another heat source is coming at this region, so or heat sink is coming at this region. So usually what will happen from this, for equilibrium, what is supposed to happen is this 100 degree Celsius region will lose the heat to the region of 30 degrees Celsius. This 100 will come down, this 30 will go up, and at a intermediate temperature, say 60 degrees Celsius, it will be at thermal equilibrium where throughout the temperature is same. Now for steady state, there can be two possibilities. When there it is in thermal equilibrium, there all the points are at say 60 degree now, so there is no heat transfer between them, and it is a steady state because there is this 60 degrees Celsius temperature is not changing with time. So that is steady state. The another possibility, what can it be? This region is at temperature 100 degrees Celsius, this region is at temperature 30 degrees Celsius. There is heat loss from the region at 100 to region at 30. However, the temperature of 100, the region at 100 should come down. However, due to some heat transfer, additional heat transfer, this temperature is kept is maintained at 100 degrees Celsius. Due to the heat transfer from the region of 100 degrees Celsius, the temperature of the region at 30 degrees Celsius should rise. However, due to some heat being carried away, like a heat sink, it is the heat is being carried away, then it is being maintained at 30 degrees Celsius. Then also it will be appearing that it is in steady state. Okay, although there is a process between them, there but because of the type of system that we are considering, it will appear that the temperature or the properties at any location are not changing with time. So that will be another that is another possibility of it being in a steady state. So this is how we can differentiate between a equilibrium and a steady state. So does it answer your question?
Yes, sir.
Okay, thanks. So then let us move on to the next problem. So now see, in this previous problem we are considering that the free surface that was now exposed to air previously now it is exposed, now a piston is attached to it. Okay, now to identify the mass, heat and workflow. So if we consider the entire, that is if we consider the initially we are considering that it is completely liquid, so after a certain after some time it certain significant amount of vapor will form which will push the piston upward. Okay, so if we consider that whatever mass inside the within the I mean below the piston is the system, then the mass will remain the same because the vapor we are now considering as a part of the system, and it is not leaving the system, so there is no mass inflow or outflow like out of the system. So considering, so like we are considering water plus vapor as system. Okay, so in this case there is no mass inflow or outflow out of the system, no mass inflow or outflow from the system. Heat flow, Heat flow will be as usual, heat inflow from bottom and heat loss, that is outflow from top and side surfaces. Now, what is workflow? See, in the previous case, as the vapor was going up, there was nothing that was restricting its motion. So, there was no work done. Here, the vapor at this particular pressure, as it is trying to move upward, it will push the piston upward. So, it will be doing a displacement work of the piston. So, we can say that there is a workflow in this case. There is no workflow into the system, but there is workflow out of the system. Workflow out of the system in the form of displacement of piston. Which is essentially called as displacement work. Okay, so I hope this is clear to everybody. So if it is clear to everybody, then we will be moving on to the next problem. Okay, so this is a pressure calculation numerical. So see, it states that what is the question here? The pressure of a gas in a pipeline is measured with a mercury manometer, having one limb exposed to atmosphere with a difference in height of mercury between the two limbs is 562 millimeter. Find the pressure of gas if atmospheric pressure is read as 761 millimeter of mercury, and the density of mercury is 13640 kg per meter cube. So what is the problem at hand? This is a pipeline through which a gas is flowing. Say it is a pressure P gas. Now the pressure at gas is measured using a mercury manometer. This is the manometric fluid, which is mercury. This is exposed to atmosphere, so this is P atmosphere. Okay, and this is the pressure of the gas at this point. So first let me tell you what is the what are the different kinds of pressure that we measure actually. So the atmospheric pressure, we take it as I mean it has been measured as 1 bar, that is 10 to the power 5 Pascal or 10 to the power 5 newtons per meter square. So with respect to the atmospheric pressure, if the pressure of a system is higher, then the difference from the atmospheric pressure, like suppose it is 2 atmospheric pressure, then the difference, that is 2 minus 1, that is 1 atmospheric pressure, that is the pressure of the system by which the pressure of the system is higher than the atmospheric pressure is termed as gauge pressure. That is, it is the value by which the pressure of a system is higher than its surrounding atmosphere. And what is a vacuum pressure? Similarly, if the pressure of a system is lower than the atmosphere, then that difference is considered to be then that difference by which the pressure of a system is lower than that its surrounding atmosphere is considered as vacuum pressure. So see, the pressure of a gas is the pressure of this gas is higher than the atmospheric pressure. So we can consider it like this. So it is a liquid column of mercury. So on one side the pressure is higher, so the force will be higher in this. So it will push the liquid column to rise in the other limb. So this difference in height is a measure of this force, and hence the pressure with which and hence the pressure of on this you can say this height difference is a measure of the pressure difference which is causing this difference in height. So this is given as 562 millimeter. See, essentially there will be a pressure drop from the gas line to this point also, but we are neglecting that pressure difference. Okay, why are we neglecting that pressure difference? See, the pressure is basically given as rho g h. So the density of mercury is like 13640. Okay, and if we considering it as air, the density will be like 1.2. So you can see it is how many times, like 10 to the power 4 times more. This drop is like 10 to the power 4 times less than this pressure drop. So this is quite insignificant as compared to this pressure drop. Hence we are not considering this pressure drop here. Okay, had it been a liquid flow, we have to consider this pressure drop as well from the gas center line of the gas pipe, center line of the liquid flow pipe to this region. But since it is a gas, we are neglecting it. Okay, so like the atmospheric pressure, it is given as 761 millimeter of mercury. So 761, so pressure is what, rho g h. Okay, so density of mercury is 13640, g is 9.81, and this height is given as 0.761 in meter. So this is the atmospheric pressure, it is given as a measure. So this comes out to be 101,828.19 Pascal. Now the pressure of gas at this region will be the pressure, atmospheric pressure, plus this, the pressure due to this fraction or this much amount of mercury that it is lifting. Okay, so this will be rho g h, and this h will be this height to which this pressure is causing the mercury column to rise. So this is 101,828.19 plus this is 13640, 9.81 multiplied by 0.562, which is given as the height difference between the two limbs. So this comes out to be 177,028.51 Pascal, or you can write it as 177.03 kilopascal. This is a very simple numerical. I hope this is clear to everybody. If there is any doubt, you can ask.
In atmospheric pressure, why we not considered the density of air?
You are asking the why in the atmospheric pressure we are not considering the density of air, because see, it is given as a measure of this thing. Okay, let me explain it this way. Suppose the atmospheric pressure it is read as 761 millimeter of mercury. Okay, so the instrument, the fluid that was used to calculate the atmospheric pressure was mercury. It was not air. Had it been air, this height would have been significantly large, like it would have been in order of kilometer. So had it been, it is just a working fluid which is being used for the measurement of atmospheric pressure. If air is used as a measurement of atmospheric pressure, it can be used. As it will be clear from the next problem, you will see that this reading will be in the order of kilometers. Okay, so very well it can be used, a air column can be used for the measurement of atmospheric pressure, but in this problem it is given that the atmospheric pressure is read with mercury as the manometric fluid or the working fluid. So for mercury as a working fluid, this height is specific, to the mercury. Had it been water, this would be something different. So it is just specific to the problem. So does it answer your query?
Yes, sir.
Okay. Okay. Then let us go on, move on to
Hello.
the next. Yeah.
What, so what is the difference between your static pressure and this absolute pressure?
Okay. So static pressure and absolute pressure, there, see, absolute pressure, let us see. Suppose this is a system in which the pressure is 2 bar. Okay, and it is in an atmosphere whose pressure is 1 bar. So the difference between the two, that is 2 minus 1, it will be the gauge pressure that we calculate usually, is the difference in pressure. However, if we consider this 2 bar itself, this is the absolute pressure, like irrespective of what the atmosphere it is in contact with, the pressure within the system is a 2 bar. It can be considered like, suppose if this system was in vacuum. Okay, suppose if the system was in vacuum whose pressure is 0, in that case, what is the pressure inside the system, that is considered as absolute pressure. Okay, so same thing, if we are replacing the atmosphere with vacuum, then this pressure inside the system, that can be termed as absolute pressure. Okay, and the static pressure, like static pressure is, if the whatever fluid we are considering in the system, if it is not moving, then it is static pressure. However, if it is moving, then there will be a pressure due to the velocity component as well, that comes as the dynamic pressure. So static pressure is essentially termed as is termed for a system when there is no significant flow within the system, or if the whatever matter we are considering within the system is not flowing. In that case, it is static pressure. So the static pressure can be measured. A static pressure, you can consider that static pressure is a it is a phenomenon based, like it can be, depending on the phenomenon, it can be a static pressure, it can be a dynamic pressure. However, the static pressure can be measured in two different quantities, like two different ways. So absolute pressure and gauge pressure, these are like ways of expressing the same static pressure. So if 2 bar is the static pressure, then we are saying that there is no flow. This 2 bar can be expressed as absolute pressure of 2 bar or a gauge pressure of 1 bar. So this same static pressure can be expressed in two different ways. So it is like a way of expression, and this is a phenomenon based statement, a phenomenon based thing. So does it answer the question?
Yeah, but you mean to say the gauge pressure is equal to the static pressure when there is no flow?
Not gauge
Am I
pressure. The
correct?
absolute pressure and the gauge pressure
Is
are
my
just
understanding?
two different expressions of the same pressure. Pressure is a particular property, right? So gauge pressure and absolute pressure are both the expressions for the same pressure for the same property value. Okay, it has nothing to do with the static or the dynamic pressure. But yeah, static pressure, for the static pressure, the flow inside the system has, there should not be any significant flow inside the system. So does it,
Uh,
yeah, please go ahead.
okay, but
Yeah, please go ahead.
uh, if you'll consider this example,
Yeah,
yeah, can I? If you consider this example, there is a flow in this in the pipe. If you will not, if this will, if you restrict the flow,
yeah,
if there is no flow in this same example,
yeah,
okay.
yeah,
So we have calculated the absolute pressure here,
yeah,
right?
we have
So
calculated the absolute pressure. Yeah,
suppose there is no flow in the pipe. So
yeah,
okay, so
yeah,
what will be the gauge pressure if there will be no flow in the same example? So
yeah.
is it like the absolute pressure, whatever the ambient pressure we have calculated, we just deduct the ambient pressure from the absolute pressure, so we'll get the gauge pressure here in the same example?
Yeah. See, whatever, if it is flowing or not flowing, has no hindrance on the calculation of the gauge pressure or the absolute pressure. Okay, this gauge pressure is just uh, a we can say that, if see, suppose if this is flowing, okay, there is a pressure here. If it is not flowing, there might be
Yeah.
a somewhat drop in the pressure at this location, okay, because the velocity, the component that was coming due to the flow of the gas is not coming in this case. However, this the pressure at this location, irrespective of whether it is flowing or not flowing, we can deduct the atmospheric pressure from the pressure calculated at this position. To, in this case, we are getting the gauge pressure only. This is the gauge pressure, because we are calculating this pressure with respect to the atmospheric pressure. I mean, sorry, my bad. This pressure is the
Right.
absolute pressure, because we are adding this atmospheric pressure. Had it been like we are not considering the atmospheric pressure, or the, we are considering, just let me write it, it would be clear. It would be clear. So supposedly we are considering that, just a minute. Okay, so supposedly for atmosphere, so atmosphere, with respect to atmosphere, so the atmospheric gauge pressure is 0, right? The gauge pressure of the atmosphere is 0, because atmosphere, there is no difference with the atmosphere, for the atmosphere. So the gauge pressure of atmosphere is 0. In that case, this height difference that we get, it will give the gauge pressure of the gas with respect to the atmosphere, this height difference. Here we are getting the absolute pressure. So if we just subtract this atmospheric pressure value, we'll get the gauge pressure, this gauge pressure value of the gas. So is
And
it,
that would be our static pressure here.
yeah, no, that again comes from the condition here. It has nothing got to do with the, it has got nothing to do with the pressure value we are calculating. If the flow is flowing, then it will be dynamic pressure. If the flow is not, if the gas is not flowing, then it will be a static pressure. Whatever this gas
Okay.
pressure we are calculating, if
Thank you.
the if this pressure difference that we have found out, this height difference that it is causing, is by a gas that is flowing, then this gas pressure, this static this absolute pressure or this gauge pressure will be termed as mm, static pressure, if the gas that is causing this pressure difference is not flowing. If the gas is flowing, then this same value will be considered as the dynamic pressure value. So is it I mean, is it a bit clear to you?
Yes, yes. Thank you. Yeah.
Okay, okay, okay. So then let us move on to the next problem. So the pressure and specific volume of atmosphere are related as PV to the power 1.4 is 2.3 into 10 to the power 5. Find the depth of the atmosphere required to produce a pressure of, this is 1.0132 bar at Earth's surface. So essentially someone asks, right, why we are not considering the pressure of the density of air here. So if we consider the density of air, you will find out what is the height required for that column of air to give this pressure. In this problem you will find that out. So you see here it is given that PV to the power 1.4 is 2.3 into 10 to the power 5. So it is like P rho to the power 1.4 is 2.3 into 10 to the power 5. This is volume, right? Specific volume. So specific volume is 1 upon density. So we are just using that relation. So rho will be P by 2.3 into 10 to the power 5 to the power 1.
Excuse me, sir.
Yeah,
Sorry to disturb you.
yeah, it's fine.
Hello.
Yeah, hi. Go ahead.
Sir, sorry to disturb you. Sir, your video is actually not. Sir. Yeah, your video of the problem is not coming, sir. Actually, it is your face only visible.
Is it so? Okay,
Yeah.
sorry. I think so
So
it
kindly
got
for.
disconnected. Yeah.
Yeah.
Okay, okay, okay.
Yes, 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 sir.
Is it coming now?
Yes, sir. Now it is coming, sir. So
Okay.
yeah, yeah.
Yeah, yeah. Thanks for pointing that out. It was somehow it got disconnected. Okay. So, could you follow
Yes,
till
sir.
now, or
Thank.
should I repeat this? Okay, just let me go repeat this one. So
It
Please
was
repeat it, sir,
okay, sir.
because
it's okay, right? So okay. So we can write it as P to the power 1 by 1.4. By this value, if we consider, it will come out to be 6757.80. Okay, now we have, if we write the pressure difference from one point to another in a differential form, then we can write it as rho g dh. The same form, this one, pressure rho g h, we are writing it in a differential form, dp equals to rho g dh. Why minus? Because as the height is increasing from the earth surface to the I mean above, the pressure is decreasing, so there is a negative sign. Now what we can write it here as rho, let us put the value of rho 6757.80 g dh. Okay, so this is a simple integration, e to the power 1 by 1.4, and this is minus 9.81, that is the value of g, by 6757.80 dh. So what we are integrating it from from height of 0, that is height of 0 from the earth surface. At that region the atmospheric pressure is the 1 bar pressure, that is sorry, 1.0132 bar at the earth surface, and at a height h we have to find what is the height of the air column, right? Like at the top surface till the pressure becomes 0. Like at a height h from the earth surface, the pressure will become 0. At the earth surface, the pressure will become p. So these are the limits. So if we do the integration, it will be like p to the power minus 1 by 1.4 plus 1 minus 1 by 1.4 plus 1, and this is minus 9.81 by 6757.80, and this is 0. Sorry, there is a mistake here. The limits, let me change, I mean, so it was written opposite, not opposite, the like at height, at depth, the pressure at depth 0, I mean when the height from the earth surface is 0, the pressure will be p, and when the height from the earth surface is h, the pressure is 0. it was just written opposite, like 0h here and p0 here. So same thing, just with a minus sign. It is like when the height from the earth surface is h, the pressure is 0 as we rise above the atmosphere. And when the
Sir, not getting.
okay, so see, this is the earth surface.
Sir, that is not getting it. You mean
Sorry, can you please this thing you are not understanding,
the
right?
integration that you said, na, the S2.
Yeah.
Yeah, yeah. That's
Okay.
what.
Okay. So the earth surface, right? So this is the height from the earth surface. Just pardon my drawing, it is difficult to draw here. So here the height is 0. Okay, height is 0 from the earth surface. We are calculating the height from the earth surface. So when the height is 0, the pressure is P, that is the atmospheric pressure that we experience at the earth surface. This one, the pressure at the earth surface. When as we move above, as we rise above from the earth surface, the pressure will keep on decreasing. So at height, some height h that we are trying to find out, the pressure will become 0. That is, it is like the air is, there is air here, right? So at this height, there will be, it is like there is no more air after that. So the pressure above it, there is no pressure because of that. At this region, the pressure of air becomes 0. So at this height h, the pressure becomes 0. Okay, so is it clear to you?
Sir, but we are using negative sign for the height, due to the decrease in pressure when we are going up. So
Yeah.
already we are using the negative sign for that. But
Yeah, that see
and
the
again we are the limit that we are.
yeah. So see, limits, the values of the limit should be corresponding to each other. It is even before, supposedly, let me, if we write, so this is the variation, like with say when dh, when height is increasing, the pressure is decreasing. So when dh is positive, the pressure difference from 1 to 2 points, suppose this is the point 1 and this is point 2, okay, from 1 to 2, dh is positive. Okay, so but dp, the pressure difference from 1 to 2, that is p2 minus p1, will have to be negative. How will it come out to be negative? Due to this negative sign, because this is a positive sign, so this cannot make it negative. So hence this is the negative value. Okay, so first thing first, so is this clear why we are putting the negative sign?
Yeah, negative sign is clear, sir.
Okay, now coming to the limits of integration. Coming to the limits of integration, so let us not confuse it any further. Let us say, okay, so the height is 0. We are integrating from height 0. So at height 0, what is the pressure? This is pressure P, right? And at height h, the pressure becomes 0. These limits should be corresponding to each other. That is, at 0 height, we should consider the pressure value which is corresponding to the 0 height, and at height h we should consider the pressure which is corresponding to this height. So is this clear?
Sir, that you are saying the depth of the find the depth of the atmosphere required to produce a pressure of 1.013 bar. So that pressure is at h or at 0.
That pressure, this supposedly, we, if we considered from the top surface, it will be a depth like this height. From, since we are considering from the earth surface, this will be a height. This same height, if we consider from the top surface, it will give the equivalent depth, right? It is just a dimension, length dimension. Had we considered from the top surface, this limits will be different. like this height we are considering, it is not the depth, this is the height from the earth surface. So from the earth surface, this height of air column will produce the pressure. It can be just simply restated as that this depth of the air column will produce the same pressure. So we are, this is the height, this is not the depth. So is it clear now? I think so. The confusion was there only. So is it clear, right? The how, why we are taking this limit? Okay, so I'm taking that this is clear because if there is any doubt, you can still ask. Otherwise, let me then go ahead uh, with this. So this is the integration from p to 0, and this will be the value. Okay, so there is some issue here. So this will be h minus 0. So if we put in the values, this will be, this is from 0 to p. So there will be a, I mean 0 to the power this value, it will be 0 only, and minus this p value. I mean when we put the p value here, so it will be essentially a minus sign here. So or to avoid confusion, let me write 0 minus p to the power, this is minus 1.4 plus 1 by 1.4 plus 1, so this is this will be 0.4 by 1.4, and this is 0.4 by 1.4. okay, and this equated to this one, minus 9.81 by 6757.80 is 7.80 h. So let me not go into the details, this is just a simple calculation. So if we put in the value of pressure here as 1.0132 bar, that is 101,320 Pascal, you will find out H to be equal to 64857.32 meters, that is around 64.8 kilometers. So this is the height from the earth surface, height of the air column from the earth surface, which is required to give us a air atmospheric to give us a pressure of 1.0132 bar at the earth surface. So the depth significantly, this can be similar, I mean the same thing can be restated as so the depth of atmosphere required is 64.8 kilometers. Okay, so as I have already previously stated, see in this problem we took 761, it is in millimeter, whereas if we consider air as a working fluid, the height of the column required is much larger, like in ranges of kilometer. So it is usually measured in a and the factor that it is deciding is the density of the working fluid. So we usually consider a working fluid which has a higher density. So I hope it is clear to everybody. If yes, then I will be going on to the next problem. Okay, so this question, what do we do for considering limbs here? I am not understanding which question you are referring to, so you can please ask. And regarding the quasi-static and non-quasi-static process, so a quasi-static process, it will be clear to you further in the upcoming classes. Uh, a quasi-static process is one such that it moves through a process from one state to another is happening in such a way such that its deviation at any point of time at the deviation from the thermodynamic equilibrium is very small, that is, it is not deviating much from the thermodynamic equilibrium. In that case, we can consider it to be quasi-static, as if it is significantly static with respect to the thermodynamic equilibrium. In non-quasi-static process, it is not the case, just that there is a significant deviation from the thermodynamic equilibrium. So let me move on to the next problem. Okay, so a wind turbine electric generator, it is mounted atop a tower. As the wind flows, electricity is generated and electrical output is fed to a storage battery. Consider the wind turbine generator as a system. Find the interactions of the system with the surrounding and find the same considering only storage battery as a system. So this is a wind turbine generator. This is the wind turbine and this is the generator. So air is flowing across it. Okay, so considering this as a system, what are the interactions that are happening? So here the system is an open system. Why? Because the air is flowing in and out of the system. It is an open system enclosing the turbine and generator, through which air flows in and out. So what are the significant interactions? Significant interactions are mass of air flowing in and out, and electrical work output from generator that is fed to the battery. So it is clear, right? And am I audible? I'm not hearing anything. So am I audible, right?
Yes, sir.
Yes, sir.
Absolutely, sir.
Okay,
Yes,
okay,
sir.
okay. So
Yes, sir.
now considering the same system, we are now considering only the storage battery. Like this electrical output is being stored to a battery. So what will be the interactions in that case? So suppose this is the battery in which electrical work is fed. Okay, and this is the system that we are considering now. This is the system, this is the battery. Now the system is a closed one. Now the system is a closed system. enclosing the battery. Okay, so the interactions, there is no mass interaction, in or out of system. There is work input to the system. Okay, but there is no work output of the system. I mean, unless we are connecting it with some other motor or a something that it is consuming the work. At this, it is just we are considering that the work input to the system is being stored into the battery. So work input to the system, no work output. And see, due to the storage of heat, due to the storage, not heat, due to the storage of energy, there can be like a battery can store it in many different forms. Like it may undergo a chemical reaction or an electrochemical reaction, and there are significant ways of storing the energy. So due to the storage of energy, there might be a generation of heat. There might be a generation of heat. And due to which there is an increase in temperature. There might be a generation of heat and increase in temperature. So there will be heat loss, that is outflow from system. To ambient, like you can consider that this is the heat loss. All this will be from all the surfaces, there will be heat loss. Okay, so this is the interaction that it has with the surroundings. So I hope this is clear. And I think somebody has kept the mic on. Can you please turn it off? I mean, if there is no query, then is it possible to turn it off? Okay. Thanks. So, okay. So these are all very simple ones. So this is essentially a property variation diagram, like how the property are changing from one point to another. So this is a very important diagram that you will be these are the class of very important diagrams which you will be using significantly throughout the thermodynamic course. So what are the different points here? So can anybody just tell me what are the points? It will be just so that I can understand that from the discussion you could understand it. So what is the point A? That is, what is this P2? What is this called? Is it a property or a state or a process? And
It is a state.
okay, why is it a state?
Because from that it is changing.
Okay, no, I was talking, it is, so the point A, it is not basically a state, it is a property value, that is, it is a pressure value. For the state of a system, you have to know what are the two different, at least two intensive properties, like two properties of the system should be specified to understand what is the state of the system. Like a pressure, suppose this is a 100 kilopascal pressure. A system can have a 100 kilopascal pressure, and it can be at 10 degrees Celsius, 20 degrees Celsius, 30 degrees Celsius, 40 degrees Celsius, at n number of temperatures. So a particular value of a property does not does not fix or does not mean a state of the system. It is a property of the system. It fixes one property of the system. So this is a property. This fixes one characteristic of the system. When we combine it with another characteristic, here we are combining it with the specific volume, which is another intensive property, we get a state, that is the point 2 has a particular pressure and a particular specific volume. So this point 2, that is the B point, is a state. The point A is not a state, the point A is a property. When two particular properties are fixed for a particular point, then we get the state of the system. So is it clear now how the difference is coming?
Yes, sir.
Okay. So what we can assume?
Yeah, all right, sir.
Yeah. So here A, D, F and G will all be properties. The pressure values and the specific volume values. The points B and E, where two properties are fixed, like this is P2 and V2 and this is P1 and V1. So these are the states of the system. And the C denotes the change from one state to another, that it is a process. Okay, so I hope it is clear. And the last problem for today, so this is a air which is entrapped within a liquid column, which is which is inverted down, which is kept upside down. So what is the air pressure inside for the pressure, if the pressure at the bottom of the liquid is 4.15 bar? So see, this is essentially the whatever we are considering, this 4.15 bar, it is with respect to the atmosphere, that is, it is a gauge pressure. That is, the pressure at the bottom of the water column is measured with respect to the atmosphere. So it is a gauge pressure. So the gauge pressure of air inside will be what? Gauge pressure of air. See that when we consider this rho gh term, the difference from this pressure to the top, we will get the difference between the gauge pressures only. From this difference in height, difference in rho gh value, we cannot get the difference from a gauge pressure to a absolute pressure. So the gauge pressure value and this height of the water column will give the gauge pressure value of air. So gauge pressure of air is equal to this pressure of water. This is the gauge pressure of water at the bottom minus this value is the height of the pressure due to this height of the water column. So this is given as 4.15 bar, that is 10 to the power 5, minus rho is density of water here. So there is a slight mistake, this is density of water here. So density of water is 1000 into 9.81 and the height is given as 30 meters. Okay, so this value comes out to be 709,300 Pascal or 7.093 bar. So if we are asked to find what is the absolute pressure of air, so the absolute pressure of air will be this is 7.093 bar, and we are assuming that the atmospheric pressure is 1 bar. Atmospheric pressure, so this comes out to be 8.093 bar. Okay, so this same thing can be reached by first converting this gauge pressure of water to absolute pressure. So gauge pressure of water in this case, if we sum this value with the 1 bar atmospheric pressure, we'll get 5.15, and if we repeat this then with this difference in height column, we will get the absolute pressure of air directly. So first, if we convert this gauge pressure of water to absolute pressure of water and then do this calculation, we will reach the same value of absolute pressure of air. Okay, so I hope it is clear, these calculations are clear to everybody. So these were quite simple, like preliminary concepts. So gradually we will be moving on. As the course progresses, we will be moving on to the more complicated problems. So I hope these were clear to you, and if there is any doubt you can ask, else we will be closing today's session.
One last question, sir. Will you please tell what is the difference between reversibility and irreversibility?
Okay, so you want to understand the difference between reversibility and irreversibility, but essentially these concepts will be better explained in the upcoming classes. Let me just give you an overview. So I explained regarding the quasi-static process, right? A system, when it is going through a process such that its deviation from the thermodynamic equilibrium is minimal. Okay, so that is a quasi-static process, and if we combine that process with a condition wherein there will be no friction, no dissipative effects, like there is no friction, there is the flow. If we consider a flow, then it is not viscous flow, like any kind of dissipation effect that can come into picture, that is not happening. Then in that case, the combined system thing can be called as reversible. That is, a system is going through a process with respect to a surrounding. At the end of the process, it can be reverted back, the system can be reverted back to its initial state without any total change in the system and the surrounding. Okay, so like if if a system is growing from this point to this point with respect to a process, some process, okay, after the completion of the process you can revert it back to its initial state, okay, and the such that the system that was initially in the same state and the surrounding that was in the initial state, the state of the surrounding, it remains unchanged. That is, this process does not change. If we go from this point to this point and then we come back to the initial point, this process, this entire cyclic process, it is not changing the final state of the system or the surrounding. That is, the system and the surrounding are can be reverted back to their initial state. Then this process will be considered as a reversible process. If not, then it is a irreversible process. So does it answer your question? It will be clearer when we the upcoming concepts are discussed, but is it clear?
Yes, sir.
Okay, so if there is no further doubt, then we can close today's session.
Yes, sir.
Okay, thank you. So I hope you will be attending the next sessions. Please do attend and make it a success. Okay, so thank you. Thank you for joining.
Definitely, sir.
Yeah,
Thank you very much, sir. Thank you very
yeah,
much,
thank
sir.
you for attending. Okay, see you in the next class. Thank you. You may leave then.
For sure, sir.